All right, let's get started. So, welcome everybody to the first SNAPP talk of the spring 2026 semester. Um, and we're delighted to have kicking off our semester, Clara Stegehuis. Um, I hope I did okay there. So Clara is an associate professor at University of Twente. She works on probability theory, graph theory, and stochastic networks, and is especially interested in topics in network science like epidemics and percolation, network asymptotics, um, and network asymptotics, and sort of geometric interpretations of network structure. And today, Clara is going to tell us about homophily within and across groups. So please, Clara, take it away.
Yes, thank you very much. Thank you for these introductions. Feel free, of course, to interrupt me for questions during the talk. So I hope that, yeah, so this work was a bit of a joint work with people from mathematics as well as from physics and computer science. So I hope that the idea will be a bit good for everyone's background here. So let's go. This is based on work which was done together with Abbas Rizi, Mikko Kivela from University of Aalto, and it has recently been accepted in Nature Communication, and Riccardo Michelan, who is now in Italy, and this was recently accepted in Nature Communications. So homophily within and across groups. So let's assume that for now that you are at a party. So you're at a party in a big house, and all of a sudden someone starts spreading a rumor. For example, the rumor that some very famous person is there. So as soon as, of course, as someone starts sharing a rumor, what will happen is that everybody at the party will meet in groups and probably discuss this rumor. So if you look at one room, maybe people are meeting in groups of four, in groups of two, well, in this case, only groups of four and two. In other rooms, maybe some people are lonely, they're just on their own, they don't care about the rumor. And other people are also, again, meeting in other groups. And as you can see, some groups, for example, in this case, are only female, sometimes male, female, sometimes only male. And this can, of course, change at every time period. So one thing that has been interesting to network scientists for a very long time is a concept which is called homophily. So, for example, in this case, if you would think of the population as male and female, one question you could ask is like, are women more likely to meet with women, or is it more like, or is it maybe more likely that that groups interact more in mixed groups? And this concept was actually captured by Coleman in I think in the 60s. And he introduced this concept, which is for a network in which all the nodes are colored. And this homophily is a sort of measure of how many nodes are in between this are between nodes of the same color and how many are between nodes of different color. So how does it work? So suppose you have a graph where every node has a color, then you compute how many fractions are between two red nodes. So there's only two colors in this specific example. So what is the fraction of nodes with fraction of edges between two red nodes, and what is the fraction of edges between two blue nodes? Now, and then in this case, so you have to so yes, and so a very homophilic network maximizes the number of edges between nodes of the same color. So for example, the fraction of links with the same color is 1. So in that case, all edges would be between the same color groups. Now, of course, this is not really, so if you only maximize edges between the same color groups, that is not always fair. So that you basically subtract the fraction of same color links that you would have if the network were formed completely at random. And depends of course in what kind of model this randomness is, but if you take one particular model of randomness, then you exactly end up at this nr squared minus nb squared. So what is so nr? That is a fraction of red nodes, and b is a fraction of blue nodes. Then there is some normalization to make sure that the maximum homophily is always 1. And for example, even in this very small clique of 6 red ones, then you can see ERR equals 1. In this case, NR also equals 1. Yes. Okay, and then we get 0 divided by 0, which equals 1. In any case, so this is a purely homophilic network. But of course, you can also, but this homophily can also be negative. So if you have graphs in which, for example, you have red, blue, red, blue, red, blue alternating, then it's possible that the homophily is negative, at most -1. Now, so this is for a graph. So it can be any graph. So this is just some measure you can compute for any graph. Now, relatively recently, a paper said, well, maybe this concept of graph homophily is not everything there is. So they were more social scientists studying specific interactions. And they said, well, what we see is that if you look at interactions of two people, then men are more likely to meet other men. On the other hand, if you look at women, apparently in this data set, they like to meet other women in groups of 3, but in groups of 2, they typically interact more with men. So women apparently group together in larger groups, men in smaller groups. So homophily is not one unique thing that defines a network. So this is something that we actually wanted to capture in a model. So what we want to capture is, so we have interactions. In this case, so the red ones, they would be male, blue ones are female. And suppose that we have data of interactions over time. And then you can think of these interactions, if you want to look at it as a network, you can think of it as a clique. So an interaction between 3 people, that is a clique because all 3 people interact. If you like, you can also view it as a hyperedge. For this talk, that actually doesn't really matter so much. So each interaction defines a clique, and if you have multiple interactions over the evening, of course you form part of multiple cliques. So we will in the end consider a network that is built on cliques, which are all the interactions, and also the nodes are colored. So for example, in this case, let's start with only 2 colors. Now, one question that we can already think of is, now suppose we look at 2 cliques. Well, in this case, there's 3 possible ways to have a colored 2 interaction. So red, 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 blue, or blue, blue. And in general, what you can say, if you have an interaction of clique size C, then there's C plus 1 possibilities for the distributions of the colors. So you can see here the example for the clique types. And now we say that the fraction so in this case, we label all these different compositions. So 0 is the composition where you have 0 red nodes. 3 is the composition in which you have 3 red nodes. And then we give all of these, then we form a probability distribution which we would like to have. So for example, you can say maybe 50% of the cliques should be all blue of the 3 cliques. And then we try to adapt this homophily. So remember, we had this equation for homophily, which works for any general graph. Now, any general graph, now we look at these clique interactions. If you just plug in cliques here, that is not so difficult because most of the equation actually remains there. So if you have a clique here, then the homophily of a clique, so we have to figure out, so how many edges are there between the same color? So if there's I red nodes in a clique, then there's I choose 2 interactions between red nodes because all pairs within a clique are connected. Then all the other ones must be blue, so C minus I blue ones. So C minus I choose 2 interactions are between blue nodes. And then we divide by C choose 2 because it should be a fraction. So this is the homophily of a specific colored clique. And as you can see, for example, in this 6 clique with all red nodes, the homophily is still 1. But if you look at this 4 clique with 1 red node and 3 blue ones, then if you compute this, the homophily would be -1/3. So so in any case, so the more similar color nodes you have, the higher the homophily. Okay, so now we can define the homophily of one single clique. That is not so difficult. And then what we say, we now say, okay, our network actually consists of different layers. So let's look now, for example, at all interactions of size 3. In that case, the network will consist of only triangles, basically. So these are all people that have met over the evening in a group of 3. And then we say that the homophily of this layer of the network is basically just the homophily of every clique type. So this HCY multiplied with the fraction of cliques which actually have that shape. So if you have many, so these are these F0, F1, F2. So the total homophily of a specific layer is just the homophily of all these possibilities times how often they occur. Okay, so now maybe I will also show, so I will now, I think one important question is how do we actually choose model these different fractions? But maybe just one example to show that why this model actually does make sense for some real data. So here I show a picture of 6 real data sets, which actually are exactly what we model. So they are all data sets of interactions in groups over time. So for example, we have this CPH. This is a network of actual uh, so this is like an actual interaction network, physical interaction networks, which was studied during COVID. There's POCAC, which is an online social dating network. And but there's also most of them are basically social networks.
Yeah. Hey,
So
Clara,
what is it?
sorry,
Yes.
there's a question in the chat from Andrew saying, you mentioned that men tend to socialize in pairs, but women in triads. Is it possible, or does it make sense to compute a homophily for each type of color? Is the question.
Yes, I think that's a very interesting question. So I think in our setting, so in the equation we use, it does not really make sense because as you can see, it's symmetric in red and blue. But in this paper that they show that they made some sort of undirected or sort of a directed homophily where so where they actually decouple this red and blue and actually make a different homophily equation that actually looks at red and blue from a different perspective. But from this equation, you can just interchange red and blue if you like. Yes, so in any case, so here on this axis, so what we see is the interaction size for the real data and the homophily as basically from this definition. And what we can see is that different networks really have different values of this homophily in different layers. So for example, what we see is that this POCAC social network has negative homophily when people meet one-on-one, but actually very high homophily, or well, not even very high, but higher homophily when people meet in larger groups. Whereas from these physical interactions, we see that people actually, meet basically randomly when the group is small, but when the group is larger, the groups seem to be extremely mixed. Why this is the case, I also do not know, but at least here from this data, we can see that really modeling networks with one layer of homophily is not always correct. So yeah. So how do we model these networks with these different homophily structure on different levels? Now, so for general graphs, actually, there is already research on how to generate random networks with a specific homophily value. So this one I'm not going to introduce so much, but it basically makes sure that you split the network in a right amount of red and a right amount of blue nodes. And then you say, okay, so how many connections do I want every node to have? I think in most cases, actually, what is also assumed is that every node has the same amount of connections. And then you match these connections with a probability which is based on this homophily. So you can compute exactly, so what is the fraction of red nodes that connect to blue nodes to get this homophily. You can do that from that equation because if you have the homophily, you know NR and NB, you actually already can figure out how many edges should be between the same color. So you can compute how many edges should be between the same color, and then you know how many should be between different colors, and then you just randomize how this pairing happens. Okay, so but we want to have one with cliques, and so we do it slightly differently. So now again, we assume that we know how many red and how many blue nodes there are. So we start with that. Then we basically sample these 3 cliques uniformly at random. So what does that mean? So for example, so we have these distributions F0 so F0 means so first I sample I hope this is here. Yes. So first I sample basically a random number based on this distribution, which tells me what kind of clique I want to sample. So in this case, with the highest probabilities that I want to sample 1 blue and 2 red nodes. So first I sample that, and then if I say I need to sample a clique with 1 blue and 2 red nodes, then I sample 1 blue node uniformly at random and 2 red ones. And I keep on doing this until I have until I reach the number of interactions that I want to have. Then, of course, from there it's not so difficult because then you just draw the 3 cliques in this case, and we have a graph again. But the question is, how do I actually get all these F things? How do we know what should I choose for all the fraction of cliques? Because otherwise we end up with a large number of parameters. So what we chose to do is to fix. So suppose that we say, okay, I know what homophily level I want to have, and I know how many number of red and blue nodes are there in my network. Given that actually we do not know anything else, so we thought that the most sensible choice for this distribution would be to calculate the maximum entropy distribution. So what that means is so the entropy of a distribution is the definition is written above. So it maximizes the entropy. So it basically, but it does need to satisfy specific constraints. In this case, the constraints it needs to satisfy. So first of all, the green constraint basically tells you so that the homophily of the resulting network should be exactly the number that I told it to generate. And then the purple is what I also want to have is that the number of red, the fraction of red, and because of that also the fraction of blue, because we only have 2 colors, fraction of red nodes is actually NR. So HC and NR in this case are 2 prescribed. So these are input to the model. And then it solves this maximum entropy problem to figure out what distribution FC maximizes the entropy over all possible distributions over, in this case, C plus 1 values maximizes the entropy. And so we can see in the plot a few examples. So in this case, that would be for a 4 clique. And we see that depending on how you specify this number of fraction of red nodes and the homophily, the distributions actually look quite differently. So this maximum entropy framework is actually able to capture quite a wide range of distributions. And so if we actually, so here this is of course a maximization problem. If you do the math, it's not actually super difficult to come up to then result in that this maximum entropy distribution has a specific shape, which is 1 divided by some normalization constant to make it a probability distribution times the exponent of theta1 times I, where I is the number of red nodes, plus theta2 times the homophily you want to attain. And then these theta1 and theta2, they depend on the input parameters. So they depend on this NR and HC. So depending on how you choose them, the theta1 and the theta2 are different. Yes. Okay, but this is only for 1 layer. So so now we have, for example, the layer with 3 cliques. Well, then for the layer of 2 cliques or the layer of 4 clique interactions, we can do the same thing. So we can say we want to generate 1 graph of interaction between 3 people, which has maybe positive homophily, 1 graph between 2 people with 2 people interaction based on negative homophily, and so on. We generate all these individual layers, and in the end, we basically just merge them and say every edge that was present in one of these layers is present in the big graph. And then we will see that the final graph is actually made of all these different types of interactions in different group sizes. And then if you want, you can again compute the homophily of the entire network just based on the homophily of all these individual layers. But I mean, of course, so the point of our work was to introduce these single layers, so this individual parameter is maybe not that interesting. Now, so before I will go to epidemic spreading on this work, I would like to share a bit on how what we actually found on the data. So again, so we used 6 data sets, which all have these clique-based interaction, and more importantly, in this case, for all these 6 data sets, also it was so every node has an attribute which is either male or female. So in this case, binary. So this exactly fits our red and blue colored approach. And then here what you see is all these 6 data sets. So every column is a data set. And then what we see are these clique types. So for example, the top row is the interactions in cliques of size 2. So the left one is only blue-blue. The middle one is blue-red, so the purple column. And the red one is how many interactions were there between 2 red people. So it's exactly the same graph as, I hope it's, yeah, maybe. It's exactly the same graph as this, where we have but here I didn't draw all the things because then it wouldn't fit anymore. So it basically tells you how many red nodes are in every interaction. Yes. So, and then all the bars, they are the data, and the dashed line, that is actually our maximum entropy fit. And I think that I think it's really remarkable that this maximum entropy fit is so well for all the data sets. So of course you can argue for the layer of 2 cliques, maybe it's not that impressive because we use actually 2 parameters, and we only have 3 values for the distribution. But actually the clique sizes go up to 20 and the fit is actually just as good over all data points. So actually from this one, you can say that people really behave as maximum entropy in a sense. One remarkable thing is also, so I showed you this data set before, maybe one example of where it really is very clear that this different layers of homophily is there, is in one online dating network, where we found that for example, in interactions between 2 people, homophily is very negative. So what does that mean? Between 2 people is basically male-female. Which actually makes sense for a dating network. That is actually what you would expect, is that most two one-on-one interaction are probably between men and women. But then we see that the bigger groups, they are actually much more likely to have people of the same gender, where it's probably like people gossiping in larger groups about their dates, or maybe warning people for specific dates. So here you can really see that this homophily does make a difference. And so we also looked at the trends for 100 friendship networks from Facebook. And there we also had male, female as attributes. And here we have the homophily per clique size. And we see basically that for almost all networks roughly follow the same trend. So that in one-on-one interaction, it actually seems more likely that it's between a man and a woman. Maybe with 3 or 4, it's basically random. But then for very large online groups, they're basically all female or all male. So there are some very interesting things in these data sets that the previous analysis of homophily, which basically for all these data sets showed that it would be like roughly 0.1, that doesn't show. Now here we just had men, women, of course. So we had this model. Of course, it's not too difficult to incorporate more colors. In that case, so we have a specific number of colors, so we don't have only 2. In this case, for example, we have 1, 2, 3, 4, 5 different colors. So then, of course, the only thing that is a bit messy is that now a specific clique type is not described by a single number, but really by a vector, which tells you how many of all these colors are in there. So in this case, there's 2 blue ones, 1 brown, 1 green, 1 pinkish, and 1 gray. Now you also have to figure out again, so what is the, again, this homophily thing for a clique, but that is also not so difficult to do. And then derive the maximum entropy distribution again, which then also depends on the vector. But this is not too difficult. But just I will just show one empirical results from this as well. So we already saw the plots on the left before. So this was the Facebook friendship networks. If we say the colors are whether you are male or female. Now on the right hand side, we also have a plot for the same Facebook networks, but now we have multiple colors. I think there were maybe 10 or 20, well, somewhere between 10 and 20 colors, which are the graduation years of the students. And then here we see that the patterns there are completely different from the male-female things. So we see here that actually, well, no matter the group size, homophily is always positive. So people are more likely to meet people from their same generation. But specifically in groups of 8 people, it seems very strong, whereas for very large groups, it's actually more likely that there's also people from different graduation years. Okay, so that is basically a model to generate networks with a specific type homophily profile. Now, the second question is, so does it actually matter, this homophily? Why do we actually care about whether a network has different types of homophily? And one reason is because we may be interested in spreading over networks. So previous research has already shown that, for example, if you look at vaccination or non-vaccinations, that there's typically also an assortative pattern. So people who vaccinate are more likely to have friends who also vaccinate, and similarly, people who don't like to get vaccinated, they also typically are more likely to connect to each other and have strong social ties with them. And that can actually influence how an epidemic spreads a lot. So one thing that was already known is if you have this homophily, so if you have that similar people, so vaccinated people meet many vaccinated people, unvaccinated people meet many unvaccinated people, then this actually makes herd immunity much harder to reach because, yeah, you always have these communities of people who don't get vaccinated, and if they interact with each other, it's very difficult to stop an epidemic there. So what we do is we study one specific version of an epidemic, which is a very simple one, but you can think of it as a model for an SIR epidemic, so susceptible, infected, removed. So with an SIR epidemic, one person starts susceptible, then starts infecting people, and everybody who is infected gets removed from the population at some point, and they never become susceptible again. So this is a very simple model for a disease. And actually for networks, you can actually map it to a much simpler model even, which is the model of bond percolation. So in bond percolation, you have one parameter pi, and you say, well, independently, I keep each edge with probability pi, I remove it with probability 1 minus pi. So these are the dotted edges, they are removed. And you can think of this as this removal that is basically, well, that this coin toss, this pi versus 1 minus pi, basically means if one of the two persons on the end would get infected, would they infect the other one? So in the SIR one, you can actually map it to the probability. What is the probability that I spread my virus to you before I recover? And this is a probability that you can actually compute for this SIR epidemic. That is not too difficult. And then after that, you say, okay, now so these capped edges, these are the edges along which an infection can spread. And the ones that have been removed are the edges along which an infection is not able to spread. And then, so if we know, so this pink person gets infected, then in this bond percolation, now we already flipped all these coins. So then we already know, okay, then in this SIR epidemic, we know that in the end, only these 4 people will become infected, because otherwise you have to cross one of these dotted edges and an infection won't spread there. So mathematically, what it means is that we remove every edge with probability 1 minus pi in a network. And after that, we look at what is the size of the component, the connected component, in which the first infected person is. And that's, if we then go back to the SIR epidemic, that is the final size of how many people have been ever infected. So how far can this epidemic reach? Now, this is for a simple epidemic. Here we have something which is slightly more difficult because we have different types of edges. And you can think, for example, if you really look at it, for example, from the perspective of vaccination, it's not, yeah, so the whole point of this is to have that, for example, between 2 vaccinated people, an epidemic is likely to spread more easily than between 2 vaccinated people. So the spreading probability between the different classes is not likely. I mean, from a modeling perspective, they should be different. So in this case, we have 3 different probabilities for an edge to be removed, and they reflect the spreading probability between 2 blue nodes, between a blue and a red one, and between 2 red nodes. And depending, of course, on the specific application, maybe they are all the same, but it's also not, in most applications, it's probably likely that they're all different. Now, so we can actually analytically derive then the fraction of vertices that will ever be infected on average. And so I will not go into this into detail, but this basically boils down to writing down a big matrix equation where we compute the average number of nodes of one clique that infects on average how many, so of one type of clique, so for example 3 blue ones, how many people. So first of all, we need to know, so what happens if we spread an epidemic within this clique? Then we get some sort of recursive equation. So how likely is it in a 6th clique that after this epidemic we spread it to 4 other nodes, or to only 3, or only 2? This is something that we can write down through a recursive equation. And then from that, we want to know, so how many new cliques will I reach? So I infected so maybe 5 people in the household in this clique. And to how many cliques on average of different types am I connected? If we compute this, then we can actually also figure out what is the condition for an epidemic to become very large and become a giant outbreak, and under what conditions will this outbreak actually be so small that the fraction of infected people goes to 0 if you have a very large graph. Now here I show some synthetic examples. So on the x-axis, there's the red percolation probability. And on the y-axis, there is the fraction of vertices that are infected in the end. So the size of the giant component. And now all these different colored lines, it's not so important what they are all exactly. But what is important is that if we just looked at the network as a whole and compute the homophily, they have the same homophily. But the difference is now, in our model, of course, we can have all kinds of different group compositions that have the same global homophily. So for example, we can have very same-to-same interactions in 2 cliques, so one-on-one interactions, but maybe very different, very mixed interactions on 6 in groups of 6, or the other way around. If you just looked at it from an average perspective, they would be the same. But here we can actually see that under epidemics, they behave differently. Also not really understandably differently. So one thing that we can see, for example, is that the exact point for this percolation probability where an epidemic starts growing exponentially, if you will, that is different for all these networks. And also the size of, so how many people will be infected in the end is also different. And actually, it's not even clear in this model that homophily actually, what is the role of homophily? So I now showed two pictures. So we have so many parameters, so it's a bit difficult to uh, figure out what to plot. But let's say that we say red, red, and blue, blue. There, the epidemic spread is the same. The only difference is between red and blue. Now, then in this case, in one case, if the red-blue spreading probability is low, so 0.1, then so this critical PRR, that is, so how infectious should an epidemic be to have a giant component? So to be so when is this R0 larger than 1, if you want? Now we can see that if the red-blue probability is kind of low, then the more homophily you have, the higher this critical probability. So that actually means that more homophily helps spreading. Whereas in the picture below, we see that so more homophily actually make this critical probability. So in the picture above, more homophily makes the critical probability lower. So the conditions for a giant component to exist become easier, so the epidemic spreads more easily. In the picture below, if we increase homophily, so this H2 or H4, then all of a sudden it becomes more difficult for an epidemic to spread. So this model that we have shows that actually it's not always true that homophily, so this being in groups, always helps or always hinders an epidemic. That really depends on many, many network parameters. Now, for example, if you look at the case of vaccination, you could, for example, say, so blue is non-vaccinated. There we have the standard epidemic. Then if you are vaccinated, so red, and you interact with a non-vaccinated probability, then depending on the efficacy of the vaccine, then your spreading probability gets lower. And if it's between two vaccinated people, red, red, then the spreading is even less likely to happen. And there, depending on how you choose the parameters, we also see that, well, this having these different groups, so having this homophily, so having that people cluster in same types or not, sometimes makes it easier for an epidemic to spread and sometimes not. So in any case, so that means that the influence of how this different homophily influences spreading processes is not something that we can just fit into a one-liner. You really have to do the work and solve these equations to figure out whether in this particular network you are maybe underestimating or overestimating the conditions for an epidemic to spread. But so in any case, so what we have seen that in many data, homophily occurs at many different scales. So in groups of 2, groups of 3, groups of 4, it may be very different. And then we can model this using a maximum entropy framework. It fits experimental data very well, and it's also not too difficult to work with because we can get mathematical conditions for epidemics to spread or not, which are not always easy to understand. Thank you for your attention.
All right, let's thank Clara. All right. Do we have any more questions? Okay, Clara, I had a basic question about the maximum entropy model. So I think I missed or didn't fully internalize what exactly are the sort of parameters. What are the parameters that are the input to the model that it is fitting? So I know this is a basic thing about just the task it's
Yeah.
completing, but I missed that. But the fact that it fits really well is very
Yes, here it
interesting.
is.
So I want to understand.
Yes, so what is the input? Is that so there's actually one global parameter for the entire network, which is the fraction of red and blue nodes. So this is something which is global for the entire network that cannot change whether you're interacting in two or groups of two, groups of three. You cannot. This is something you cannot change. Another one which is prescribed is say we want to generate a network with on clique layer with interactions of 3 has homophily 0.2. So this HC is also prescribed for every layer. What is not prescribed is well, the distribution basically. So there are many ways of getting one average homophily. For example, you can have either maybe homophily of 0 would be 50% blue cliques, 50% all red cliques. But you could also do 50% two blue, one red, and 50% two red, one blue. So we would prescribe the 50%, or no, sorry, we would prescribe, well, the 50%, no, we would prescribe the homophily value. So for example, we want to say we want to have a homophily of 0, and then the maximum entropy model decides like how to balance this out among the different clique sizes.
I see. I think I was getting confused between the two, like just the superficial similarity between the two graphs with the axes. So in one of the in for the one of the graphs, you have which layer or like how many layers are you talking about? And that graph is the input. And then you also have the graphs where the x-axis isn't really ordered. It's the
Yeah,
different types of cliques, and
yeah,
and that's the output, and you get this in very good match. That's very cool.
yeah. Yeah, indeed. So per what is it, per column? So every column has one input value, which is I want so this layer to be homophilic of 0.1, this one minus 0.6 or something. And then the entire data set also has one additional parameter, which is how many red nodes there are or how many blue.
Great. Thanks for explaining. It's a lot clearer now. This is great. Yeah, any other questions? Okay. Well, in that case, let's thank Clara one more time. Snap will
I
return.
think there's one
Oh, there is a
question.
question. Oh, sorry. I'm
Even
so
with
sorry,
the
Andrew. Yes.
same overall homophily, yes. Yes, for different click homophily, the percolation, yes, it can be very different. And that is indeed exactly the plot, which is somewhere.
So, Clara, I'm just going to read the question aloud for the future YouTube
Yes.
audience. So, the question is to clarify, even with the same overall homophily value for different clique homophilies, the percolation threshold can be quite different. Do you have an intuition for why this is the case?
Yeah, so it can be quite different, and you can see it here. So these are all networks with the same overall homophily. So in this case, there's only two click sizes, so 2 and 6. Yeah, of course, you can add even more, and then the picture, there would be even a wider range. Um, yes. So it's a bit tricky because there's actually an interaction between well, there's a very complex relationship because we have so many parameters. So on one you can have more likely to spread between nodes of the same color or not, depending on how you choose these percolation parameters. And also then you have how they are grouped. And I mean, there's some sense of, in some case, so having groups in some sense helps because then if one path of spreading is broken, well, you will infect someone through another path. So if you have a group, it's more likely that this entire group will get infected. On the other hand, if you are too homophilic, then maybe an epidemic only spreads in your tiny bubble and will not reach the other nodes. So there's this trade-off that homophily in some cases helps you um, because it adds some additional connection, additional spreading paths within a group, but it can also hinder you if you are too clustered and you don't have any links going outside anymore. And I think that this is what is happening here because the 6 cliques are larger, and if you are too homophilic there, then I think you don't have many connections going outside left. That is my intuition, but I'm not 100% convinced.
All right. Thanks for the question. Any other questions before we wrap up? All right, then let's for real thank Clara one more time. Thanks for kicking off our Snap season, Clara. Snap will return in March. Um, in March for a talk by Max Roginski. So you can see the full Snap schedule on the Snap website. So looking forward to see you at future spring talks. All right, take care, everyone. Bye.